Okay, so new chapter, Fermat's theorem. This Fermat's theorem is actually Fermat's little theorem, which is different from that famous Fermat's last theorem which mathematician Andrew Wiles proved. Most of us probably already know what this theorem is and how we apply this in many situations, because we may have come across it in algebra. But anyway, we are going to see what this is again from a number theoretic point of view, and we will also prove it not using tools from algebra, because what we see in algebra when we prove Fermat's theorem, that mostly uses group theory. Here, however, we won't use that method. We will use elementary number theoretic method to prove the theorem. But those things will come afterwards. Instead, the chapter starts by discussing one of Fermat's factorization methods. In fact, that's not exactly how the chapter itself starts. It starts first by discussing a little history on Fermat himself. That part I am not going to do. You can see the text and you can see the history there. Instead, we are going to start from the factorization method of Fermat. Okay. Now, what do we know about factorization so far? We don't really know much. We have, however, already come across one observation. So, let us start by recalling that observation. It is this thing. Suppose that n is a composite integer, positive integer of course. Then this is what we observe. Then there exists a prime number p which divides n, and p is at most square root of n. This observation helps us because n can be somewhat large, but square root of n is smaller than n, and also not a little smaller than n, somewhat significantly smaller than n, because it's square root. It's not like n minus 2 or n minus 3, not like that. It's square root of n. So, if n is composite, then you get a prime factor of n which satisfies this inequality. That means you do not have to go all the way to n in search of a prime factor. Okay, you just have to look at the prime factors that do not exceed square root of n. So that gives us a little advantage. But of course, we have already seen, we saw this when we were studying primes. We saw that as n becomes large, so does square root of n. So this little advantage there, it does not really remain an advantage anymore. But still, this observation helped Eratosthenes to come up with that sieve of Eratosthenes, which in fact lets one calculate all the prime numbers less than a given number. In fact, we also saw how it can be used to say find all the prime numbers less than 100. But still, this way of trying to find factors of n, if n is composite, then it will have non-trivial factors. And by non-trivial factor, I mean a factor which is different, which is a positive integer, and that is different from both 1 and n. Okay, so this way of searching for such factors quickly becomes impractical as n increases in size. So, can one come up with something else, some other type of method which avoids these things, which avoids in fact prime numbers altogether? Yes, and one such method is Fermat's factorization method. So, let us see how it goes. This is how it starts. In the beginning, we are not going to say composite prime anything. Let's just first see what the thing is, and then how that discussion can be used to see whether n is prime or composite, and also if it is composite, how we can use our thing that we are going to see here to find non-trivial factors of n. We may not immediately be able to find prime factors of n, but we will at least find a factorization of n which is non-trivial, that is, which involves non-trivial factors, and then we can apply our method to those factors, and that way we can have a complete factorization. So this is how it starts. Let n be an odd positive integer. Why this restriction odd? That's because if you start with an even number other than 2, then you already know that it's composite, fine. But that doesn't by itself tell you the full story. For example, if your number is 12, you know that it's composite because it's even and not equal to 2, it's greater than 2. And in fact, you immediately get this factorization, right? But if you really want a full factorization, you are not satisfied with this. You know that 2 is prime, but 6 is not prime. So you want to factorize more, you want to decompose it more, and you get this. So you get 2 square times 3. Now the observation that the 2's can be recognized in the beginning itself makes us choose an odd positive integer, because you can just simply repeat the procedure n number of times until you get an odd number. By the time you get an odd number, if that odd number is 1, then your number itself is a power of 2. 2 is the only prime factor, there is nothing else. That's not the case here, of course. Here instead, the odd number that we have got is 3, which is itself a prime. But that need not be the case, of course, always. For example, consider this 90. So this is also even, and this is 2 times 45. Now 45 is odd. Okay, so we cannot take out any more 2. But 45 is not prime. So the question now becomes this, that what about the prime factorizations of that part of the integer which remains after you take the power of 2 out of that integer, which is the largest power of 2 that divides the integer. In this case, that largest power is 4. In this case, that largest power is 2. And that is why this is where we should focus, and that's where we start. Okay. So let n be an odd positive integer. Now suppose there exist integers x and y. Such that n is equal to x square minus y square. Then of course, using your elementary algebra, n can be written as x plus y times x minus y. Now that may help you in finding non-trivial factors of n. I say may help you because note that we have not started by assuming that n is composite. N may not be composite, and this factorization of n may be the trivial factorization where we get n times 1. Let's also, because we are talking about these things, let's also recall what a trivial factorization and what a non-trivial one are. This is a trivial factorization of 6 times 1, because it involves only the trivial factors 1 and 6. However, this is a non-trivial factorization where the factors are both different from 1 and 6. This may actually be the trivial factorization, who knows, and it will be if n is prime. But if n is composite, then also it may be the trivial factorization. That will entirely depend on what x and y actually are for that given n. However, this method will let you, it will give you a chance to find factors of n that are non-trivial if n is composite. Now, if we go in the other way, assuming that you have factors of n, conversely, suppose that n is AB for integers a and b which satisfy these inequalities. Here also we are not saying n is composite or anything, we are just saying that n has an expression which looks like a factorization. That may be non-trivial, that may be trivial, that will depend on a and b. Okay? Because you can see that here you may have b equal to 1, then a is equal to n, and you have a trivial factorization. But then again from elementary algebra you have this. Okay, because if you expand these things and then do the calculation, you will see that this is just AB. Now you will note that since n is odd, so A and B both must be odd, because if any one of them is even, then n also has to be even. And this oddness of A and B tells us that A plus B is even and A minus B is also even. And that is why when we divide these integers by 2, the fraction or the quotient actually is not a fraction, it's again an integer. Since n is odd, so are A and B. Thus, this and this are integers. So we see that if for n this Diophantine equation has a solution where x and y are integers, then n can be written as a product of two integers. Conversely, if n can be written as the product of two integers, then that Diophantine equation has the solution x equal to a plus b over 2 and y equal to a minus b over 2. Okay. This means that being able to write n like this is equivalent to having a solution of this Diophantine equation, is it not? If there is a solution, then n can be written like this. Conversely, if n can be written like this, then there is a solution. So instead of straight away looking for ways of writing n as a times b, we can also look at this. Okay, and how do we use this thing to find factors of n? That is the next question. So this is where we next see how we can use this discussion to find factors of n which are non-trivial if n has such factors. So in fact, let's just write this in words. So n is equal to ab if and only if the Diophantine equation n equals x square minus y square as a solution, or equivalently the equation x square minus n equal to y square as a solution. As a solution where x and y are integers. That's understood. And this is what we are going to use. B, first look for the smallest positive integer k such that k squared minus n okay, let me just write like this first. That will come afterwards what k square minus n is, but first of all k square needs to be greater than or equal to n. Why do we need this? Because otherwise if you put k here in place of x, then k square minus n will be negative, and so there is no possibility of that negative being the square of an integer, obviously, because when you take the square of any real number, and in particular any integer, it is always non-negative, it's never negative. That's why we need a k, we need first of all to apply this method, we need a k whose square is at least n, and we choose the smallest positive integer k, which satisfies this. Why? Because we do not want to lose any k that may give us a square when you consider k square minus n. We want to consider all the k's that are possible, that are possibilities for giving us squares. Oh, and by the way, how do we know that such a k exists? Well, we know that because k itself needs to be greater than or equal to square root of n. So you just choose some positive integer which exceeds square root of n. Why do I say some positive integer? Why not the smallest? I am coming to that smallest. Okay. If you consider this set let S be the set of all positive integers. I is a positive integer such that I is greater than or equal to square root of n. This is a subset of the set of all positive integers. Why is this set non-empty? That's because there is no largest positive integer. And in fact, the set of positive integers is unbounded as a subset of the set of real numbers. So any real number you choose, say here square root of n, there is a larger positive integer. And that is why this set is non-empty. S is non-empty, but at the same time S is of course a subset of the set of positive integers, which sometimes we call the set of natural numbers. So by the well ordering principle, this S will have a smallest element. That smallest element is this K. Okay, that is why it exists. All right. But then what do we do? Then we take higher and higher values of x. I mean, we start with k, but then take k plus 1, k plus 2, and we look for a square when we consider the numbers x square minus n. We then look for a perfect square among the following integers: k square minus n, k plus 1 square minus n, and so on. Now obviously you can see one thing, that as this x value increases, so you can, I mean, this difference itself will become larger and larger, because this minus n stays minus n, but this part is increasing, so its square is also increasing. So you subtract n from that, that is also increasing. However, this cannot go on indefinitely. I mean, you are looking for a perfect square, okay, you are not getting, say, k square minus n is not a perfect square, it's not the square of any integer. So is k plus 1 whole square minus n, that's also not a square. K plus 2 whole square minus n, that's also not a square. Will this process ever come to an end? Because you see that there is no end to you taking larger and larger values of x starting from k. You can continue to take larger and larger values. But if you never get a perfect square, then what will happen? Actually, that will never happen because of this. This process cannot go on indefinitely though. Because we eventually reach this situation, this state. What state? This state. You are going on taking higher and higher values of x, but you will, no matter how large n is, eventually reach this number, n plus 1 divided by 2, and note that since n is odd, so this is again an integer and this is also an integer. Okay, so you do get a square eventually. It's not that you will never get a square. You do get a square, but the corresponding, this is after all what? This is again n equal to x square minus y square, where this is x and this is y. But then what is that corresponding equation where you write n as a times b? This equation corresponds to the trivial factorization. N equal to n times 1. Now, in your search for a perfect square, if you have got to this stage, and this is the first time you have encountered a perfect square and not anywhere before that, then n has to be prime, because any other occurrence of perfect square before getting to this equation would have meant that n has some other factorization. But if this is the first time you are getting square, then the corresponding factorization of n is this. So then this is the only factorization. In that case, n is prime. If okay, let me keep the language simple. If no perfect square was encountered before this equation, then the only factorization of n is that. So n is prime. Otherwise, if you really encountered some square before this, then that corresponded to some other factorization, and in that case n is composite and you have found a factorization of n. That may not be the full factorization. Every integer is not like 2 times 3 equal to 6, so that if you split it as 2 and 3, that's the job is over. There may be many factors, so you may have to apply this method then on those factors. Now let us see one example where we apply this method. And in fact, the letter in which Fermat communicated this method to Father Marin Mersenne, he used the method to factorize this number, and the number is somewhat large, 2027651281. It turns out that this is equal to 44,021 times 46,061. And again, let me remind you of something. When you see this type of notation, do not mistake it as decimal point. Decimal point always appears at the bottom. not in the middle. In the middle, if you see a dot, it's most likely your ordinary multiplication. Unless you are doing abstract algebra and this represents some exotic binary operation, that's a different thing. Usually this is how it appears. It's C dot, central dot, not L dot, which is your lower dot. Okay, so, and Fermat applied his method to find this factorization, and to do so, he had to apply the method. Apply the method means going through those numbers, x square minus n, in search for a perfect square in only 11 steps. Now imagine trying to find out such factors or some other factor of this number by using that square root method. How large this number is, and you also will have to know all the primes that go up to the square root of this number. That itself is, it's a heavy task, right? You need a knowledge of those primes. Here, however, you see that you do not actually have to know any prime. And the author mentions that this is probably a favorable case where not many steps are needed to find factors of the given number. But it shows the main strong point of this method, that no knowledge of primes are needed at all to find factors of a number if it is composite. But it's not always that one will get factors in so few steps. Actual factors may come out after applying this method, and it may take many steps actually. This is a favorable case which shows that in some cases this method is a very good method. Okay, so this is not the example. Now let's see the example. This is Fermat's example, but the text offers us this example. In 8, the number in question is this n, 119143. So in order to apply Fermat's method, first of all you have to find the least number whose square is greater than or equal to n. And this is what it's given in the text, that 300, you can verify that this is the case, that the square of 345 is less than the given number, but the square of 346 exceeds the given number. This is less than n, but this square is greater than n. So that k with which you have to start your method is this 346. So that means what do you have to do next? You have to next look at these numbers. 346 square minus n, 347 square minus n, and so on. Now when one starts calculating these numbers, now and there is one more thing that you may have a little difficulty with, and that thing is that whatever number you are getting as the difference, you have to decide that it is a square or it is not a square. That itself may involve some other calculations. Okay, you may have to use some other observations from whatever elementary number theory we have already seen. You may have to use those other observations. For example, let us recall something which we saw long back when everything started, right? When we studied the division algorithm and its consequences for the first time. There, we came across this, no? Every number you know is either even or odd. Integers, of course, I am talking about. So every number is of the form 2k or 2k plus 1. Now when you square an even number, what do you get? You get 4k square. In other words, when you divide an even number by 4, the remainder is 0. Whereas, when you take the square of an odd number, you get this. And this is of the form 4 times an integer plus 1. So when you divide an odd number by 4, the remainder is 1. In other words, the square of any number, not this n, I mean this is something, let me call it n, is congruent to either 0 or 1 modulo 4. You may use this fact to rule out many numbers here which appear as differences. I mean, you can just see what their remainders are when they are divided by 4. If that remainder is neither 0 nor 1, if it is, there are two other possibilities, 2 and 3, then you immediately know that they are not perfect squares. So you rule them out. However, if they are in fact congruent to 0 or 1 not 4, that itself does not tell us that they are perfect squares. But this little observation may help you rule out many things here. But in any case, it turns out in this calculation that if one continues like this now, then eventually one reaches this. 352 square minus n turns out to be equal to 69 square. So here we get a perfect square. And using this equation, of course, we then get n equal to 352 square minus 69 square, or 352 plus 69 times 352 minus 69, and this turns out to be 421 times 283. So that way you get a factorization of this number in only a few steps, I think in 7 steps. But again, I am repeating that this is not always the case. One may have to really look at many numbers before one even gets a square, and that gives you a factorization. However, if your number is, let me just make one more remark about this. You obviously will want to know whether a large number is factorizable or not in a non-trivial way, or in other words, whether it is composite or not. If it is not, okay, then you will have to go all the way up to n plus 1 divided by 2 as your x value. You will start with k, then like that k plus 1, k plus 2, like that you will go. You will have to go all the way to n plus 1 divided by 2, and until that stage is reached, if you do not get a perfect square, I mean you won't get if the original number n is prime, then you are sure that n is a prime. This, however, becomes again quickly impractical because so many numbers you have to go through, and each number has to be checked whether it's a perfect square or not. That may itself be a heavy task, but it is what it is. If you are lucky, and if the number is really composite, then in only few steps you will get a factorization, and then you can apply that method to the factors and then continue like this to find the full factorization of your number. Okay, so but that so this example itself shows that there are some disadvantages. But the main advantage of this method is that you do not need to know about primes at all, okay, in order to find factors of a given number or its full factorization. So let me just end the video here itself with this. There are many other things that will come after this. There is in fact a generalization of Fermat's method itself, which will give us a little more advantage in doing all these things. That we will see in the next number theory video. And our next upload is this next Saturday. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.